Here are a couple of quick technical notes about the dot product. The first thing is to look at associativity with products here and ask whether we can do a dot product of two vectors, v1, v2, and then multiply by 3, v3, and would that be the same as if we took the dot product of the last two and then multiplied by the first? And in general, this is not going to be true. I'll put a big X through this, because this is mixing two different kinds of products. This dot product gives us a scalar as the result, and so this vector on the left here will be a multiple of v3. Meanwhile, this right-hand side is going to be a scalar here, then times v1. So what we're going to get back here is a multiple of v1. And in general, v1 and v3 are not going to point in the same direction. Then those two can't necessarily be the same in every case anyway. So let's say this could point. They could point in different directions. Which tells us that this equality is not true in general. v1, v3 could point in different directions, so this equality will not always hold. So this is where we get our first experience with a vector idea that doesn't match what we've seen with scalars. If we had three numbers, 2 times 3 times 4, it wouldn't matter if we multiplied them 2 times 3 first and then 3 times 4 later. But because here we're talking about two different kinds of products, dot product for these two vectors and here versus a scalar product with a vector, there we have to be more careful about how we define our multiplication operators. And they don't work in quite the same way as we would have seen with scalar values. Another thing we can do with dot products as a technical exercise is ask whether vectors are perpendicular. We've seen a little bit of that already. But we can also talk about the size of the angle instead. Let's take a quick look at these three vectors and then explore how we can determine the range of angle in between them. Notice they're all three-dimensional vectors, so they're in R3, and so it's not obvious what the angles would be. We can't really sketch these and estimate angles, but what we can do is compute their dot products. And so here the dot product of A and B would be 1 times 1 plus 0 times 3 plus negative 2 times 0, and that just turns out to be 1. We can also look at the dot product of A and C, not A and B again, that would be a little boring. A and C will be 1 times 2 plus 0 times 1 plus minus 2 times 1. And that, plus 2, negative 2, that ends up being 0. And last but not least, B times C would be 1 times 2, 3 times 1, and 0 times 1. And notice when we have scalars, we use this dot earlier, all throughout the course in fact, as a product marker. When they're scalars that we're multiplying, it doesn't make any difference whether we just write them as brackets or put a dot. The only time it matters that this is a dot versus some other kind of product indicator is when the two elements we're multiplying are actually vectors. Calculation here gives us a 5. All right. So we have three values that come out of this, and one of the values right here tells us that A and C are going to be perpendicular to one another because their dot product is 0. A and C are perpendicular. And let's look at why. It's because A dotted with C is also equal to the length of A times the length of C times the cos of the angle between them. And we know this is a positive number, this is a positive number, but we've said the whole thing equals 0. That was the value we computed. And so this must equal 0, and so the angle must be 90 degrees or pi over 2 radians. That gives us the perpendicularity for this particular combination of vectors. But what about these other two? Well, we can make exactly the same comparison here. We can also write this value as the length of A times the length of B in this case, times the cos of, let's call it the theta AB here, to indicate the angle between A and B. And again, if we look at the signs across here, the lengths of A and B are always positive. They're lengths and magnitudes. The smallest they can ever get is 0. But the overall dot product is 1, which means this must be positive. All right. Let's take a look at our graph of cosine here for a second. Let's do cos of theta versus theta. Graph of cos looks like this. The 0 marker, what makes cos equal 0? An angle of pi over 2 does that. And so if we get a cos value that is positive, this is the range where cos theta is positive. So 0 to pi by 2. 0 to pi over 2 gives us an angle, or a cos of that angle, that's positive. If we ever got a negative value for cos, then this would be theta in the range pi over 2 up to 180, which is pi, or an obtuse angle if you like that kind of terminology. So what this value here of the dot product being positive tells us that the lengths are positive, so the cosine of the angle between A and B must be positive. And if we see a cosine that's positive, the angle must be in the range 0 to pi over 2. So the angle between A and B must be between 0 and pi over 2 radians. If this had been a negative number, then we would have known that the cosine would have to be negative because these are positive. If this answer on the left, the dot product, is negative, then the cosine must be negative, and that would happen with an angle between pi over 2 and 180 pi. And likewise down here, this is positive, and so cos of the angle between B and C, it's a B, it's a C, is positive, which means that the angle between B and C is between 0 and pi over 2. And that's a useful tool to have in our toolkit when we're looking at geometric problems. Again, the value of a dot product being 0 is the by far the most common use of the dot product, looking for perpendicular vectors. But we can get extra insight just from the sign, plus or negative, plus or minus, of a dot product as well. It tells you whether you're dealing with acute or obtuse angles.